Okay, guys. Picking up example 5F in lesson 7-1, talking about a summer internship, talking about the grape juice in the vat. So, suppose there were 4 inches of grape juice initially. In order to estimate the depth after 1 hour, we will assume that the rate remains constant for the first hour. How did we arrive at an answer of 8 inches? Use this technique to complete the chart.
Can we just add 4 every time?
Well, not every time. That's what I'm trying to...
Would you just plug it into like 2 times the square root of 1?
Well, if you go, if you go back up and look, we used that chart in part D, right? Where we use the 2 square root of y, okay? So the 2 square root of y doesn't find the depth, it finds the rate the depth is changing. Does that make sense? Okay, so it's not finding the depth, which is what we're looking at here. It's finding the rate the depth is changing. Now, so, and they say, let's see, what was it? There was 4 inches of grape juice initially. In order to, now notice, it did say, did you guys catch here? Estimate. Okay, so we're not talking precise science. In order to estimate the depth after 1 hour, we will assume the rate remains constant for the first hour. How would we arrive at an answer of 8 inches? Okay, and the idea here is, go back up here. If, what am I doing here? Sorry. Let's see, what were we? We started with 4 inches, and then the rate remains constant for that first hour. As it goes from depth of 0 to 4 inches, the rate the depth is changing at 4 inches is what? 4 inches per hour, right? So if at 0 hours the depth is 4, well, when the depth is 4, what's it say? It's changing at 4 inches per hour, so, you know, in that first hour, as you go from, as you're at a depth of 4 inches, it's changing at 4 inches, so add 4, and that puts us at 8. Okay? So when it talks about the rate remaining constant for the first hour, we're talking about adding the 4 inches there. And I'm going to go ahead and write this out here, and then we can talk about the rest of the chart. At, what's our variable y? I use d. We don't have a d in this problem, do we? In my notes, I have at d equals 4 inches. I guess that stands for the depth. Okay. Okay, so at the depth of 4 inches, so based on the chart above, the rate is increasing, and that is 4 inches per hour from the chart above. And so doing that magical math there, 4 plus 4 equals 8. And that's where that 8 comes from right here. Now, I will say the key is to catch on that it does say estimating. Okay? So basically, I guess to get this 8 here, it was 4 plus 4. Now, okay, what about 2 hours? We are currently at depth of 8.
Close to that.
Yeah, so, and that's the deal. That's why this is an estimate, okay? We only use perfect squares up here, right? Okay, so we don't have the depth of 8 because that wasn't a perfect square, but 8's close to 9, and at 9 inches, the rate is changing at 6 inches per hour, so we would add another 6 inches on. So 8 plus 6, which is 14. Does that make sense? Okay. So now we're at a depth of approximately 14 inches. What is my rate going to be close to? Yeah. So at 16 inches, the depth is changing 8 inches per hour. Now, technically what that means, the rate's going to be changing a little less than 8 inches per hour, right? But we're estimating. So now we're going to do what? The 14 we're at, plus the changing of 8, and that's going to put us at 22. Keep going. At 4 hours, let's see, at 3 hours, we're at an estimated depth of 22. What are we going to do?
Add 10.
Probably add 10. And 22 plus 10 is 32. Keeps getting a little farther off each time, doesn't it? But at 32 inches, that's close to 36 inches. So adding 12, and that is 44. And then add 14. That puts us at 58. Okay. If it didn't say to estimate, if it wanted exact, we'd be going back and finding the exact rate of change using our formula, not just the estimation, to find these numbers. Okay? Okay. So that gives us our time in hours. And it gives us our estimated depth of grape juice in inches. Yeah, and keep these numbers handy because I'm pretty sure we need them here in a moment. Okay. G. How many functions would satisfy your differential equation? Remember a little bit about what we talked about yesterday at the beginning? Problem with breaking the lesson into 2 days, right? Okay. We talked about differential equations in the beginning. And we talked about the general solution of a first order differential equation represents a family of curves. When we got to the second page of notes, we looked at several different, equations that would satisfy one. If you look down at example 4, the differential equation dy dx equals 3x squared. The general solution we found was y equals x cubed plus c. And what's c represent? Some constant, right? Okay, some constant, we don't know what it is. How many different constant options would we have? A lot? Yeah, there'd be an infinite number of options, right? Because the idea is when you put that constant on there, that constant is really just moving your equation up and down, moving your graph up and down. And so how many functions would satisfy your differential equation? Well, I have exactly that, infinite. Okay. What information determines which particular solution you find? And they didn't really have us find any here. Well, we did find one on C where they gave us, I'm trying to think, what did they give us? I say we had to find the K there, but they gave us a set of, what was it? Did they give us the initial information? Is that what I'm thinking? They gave us the first depth there. Okay. So the idea is what information determines which particular solution you find. They're going to have to give you some piece of information. Generally speaking, what piece of information do they give you? That initial condition, okay, or initial value. And so that's going to determine which particular solution you find. Okay. Officially, this says, use the data from the second table, so part F, the table we just did, and plot this particular solution of the differential equation using a blue colored pencil on the grid below. And you'll notice we're going to use green here in a little bit. Okay, so if you want colors, I knew it was coming. I got them out for a reason, right?
Grab me one of it. Yeah.
Blue and green, or make it whatever color you want and just, circle it there.
It's the ugliest green I've ever seen. Buggers.
Okay, so plot this particular solution. So folks, you're using these numbers here, 0418 all the way up to 658, and you are plotting them on the graph. Okay? So, I'm going to have to flip back here. First value is 04. What are we doing, guys? Left to right 0 and up 4. Now, you have to look at where you're graphing. Ignore all these little diagonal marks. We'll talk about those in the end. 18. Right 1 up 8. 214. Right 2. Up 14. Very much ballparking it, right? 322. 432. 544. And 658. Okay, guys. Now, notice it says use this data, plot this particular solution. So here's what you're looking at. If you can play connect the dots now, generally speaking with a curve here. Okay. There's your equation. Okay. There's your differential equation. That is one representation. Now, if you look onto part H, what does part H ask? Using a green colored pencil, plot another function that also represents a particular solution of the differential equation. Okay, move all the points up or down, some appropriate number, right? Okay. I don't know, what do we want to do here? Actually, do we all have to do the same thing?
No.
No, we don't. Moving up 6 and going to the 10. That's funny because I think that's what I did in mine. So, because my first dot in my notes is at 0, 10. And that is moving each dot up 6. Now, if done correctly, what should it look like? Yeah. I want to use the word parallel. I can't use the word parallel because they're not straight lines, but they should be equidistant all the way around, right? I'm not sure mine's exact, but you know, you get the idea there. Now, to finish up, and this is leading us into lesson 7.2. Okay. Do you notice a relationship between your graph solutions and the slope field in the background?
Yes.
Explain your thoughts.
Your angles.
Okay. Are we kind of tracking along those slope field?
Inverse.
Okay. And here's what that is. That slope field, which is what we learn about in lesson 7.2, it's the slope at that particular value. Okay. So each of those represent little pieces of the slope. Okay. Obviously, you know, down here right above the x-axis, the slope is not as steep. Up here, the farther you go, the steeper it gets, right? And so the idea is when you are drawing here, you know, mine's not perfect by any means, but the idea is you should be kind of following along that slope. And so every place that slope, those slope pieces are, you should be kind of parallel to them. Okay? Let's see. So explain your thoughts.
Slope of curve. Slope fields.
I have slope field looks like small tangent lines at some x values, or at time. And these are the rates of how fast the depth of the grape juice is changing at a specific time. Because slope is going to be the rate, right? Okay, so you can write as much or as little as you want. I'm going back to this page where I left room here. So slope fields looks like small tangent lines at some x values. Keeping in mind in this case our x values are time. Okay. These are the rates of how fast the depth of the grape juice is changing. These are the rates of how fast the depth of the grape juice is changing at a specific time. Okay, guys. You have some work done. I'm going to suggest you use it because that's only the halfway bell.
You please quit drumming with the pencils.